Welcome to this explainer. I am so thrilled to have you here today because we are setting out on a truly fascinating journey together. We are going to build a mathematical bridge, chapter by chapter, concept by concept. We're starting with the simple, familiar territory of a basic graph, and we're going to walk that path all the way across to one of the absolutely most powerful concepts in mathematics, the derivative. It's kind of like reading a great story where every single piece perfectly sets up the next. And to make sure we don't get lost, here is our map for the journey. We'll be hitting mapping graphs and roots, crossing versus touching, the geometry of slope, equations of straight lines, and finally, the derivative connection. Let's get right into it. Section 1. Mapping graphs and roots. Okay, let's dive into this. Our very first foundational building block is understanding the physical space of a graph. When we talk about a function, usually written as y equals f of x, it's basically a literal map of coordinates. Now, within that space, we have some VIPs, very important points, and we call those roots. A root is simply a specific value of x that makes our entire function equal to exactly 0. So, if we take an equation like y equals x squared minus 1, and we set that whole thing to 0, the math tells us that x equals negative 1 and x equals positive 1. Those two numbers, those are our roots. But I really don't want you to just think of roots as abstract algebra. Actually, scratch that. This is one of the most crucial ideas to grasp early on. Roots are physical meeting points. Imagine our graph is a little winding road. A real root is the exact geographic coordinate where that little road physically intersects with the horizontal x-axis. Because the x-axis is exactly where y equals 0, finding a root means finding precisely where our road hits the ground. Section 2. Crossing versus touching. Now, the behavior of our line at these roots brilliantly illustrates this kind of hidden rule in the math. It's all about the power or multiplicity of the root. When a root appears an odd number of times, say a factor of x minus 2 raised to the power of 1 or 3 or 5, the graph treats the x-axis like a border and boldly crosses right over it. But if the power is even, like an x minus 2 squared, the graph just comes down, gently touches the axis at x equals 2, and turns right back around. So simply put, odd multiplicity means crossing, and even multiplicity means touching. Which brings us to a really fun question. Imagine you check 2 points on our graph. At point x1, the function is positive, meaning the road is above the x-axis. But at point x2, the function is negative, meaning it's below the axis. So what does that mean graphically? Well, if you start above the ground and you end up below the ground, you had to cross the surface at some point, right? There's no magic teleportation. You absolutely must have crossed the x-axis an odd number of times to get from positive to negative. We can actually use this logical trick, which is tied to the intermediate value theorem, to physically hunt down roots. It's a super practical method called root bracketing or bisection. Let's say we know our function is positive at x equals 1 and negative at x equals 5. We know a root lives in there somewhere, so we test the middle. We check x equals 3. If the answer at 3 is positive, well, we know the root must now be trapped between 3 and 5. We just keep halving the distance, continually narrowing our interval until we trap that root exactly where it lives. Section 3. The geometry of slope. Slope, usually represented by the letter m, is simply a measure of movement. It's the change in y divided by the change in x, or as it's famously known, rise over run. The absolute best way to visualize this is as a little staircase connecting point 1 to point 2. If you're at coordinate 1, 2, and you walk to coordinate 4, 8, you had to run horizontally by 3 units and rise vertically by 6 units. 6 divided by 3 gives you a slope of 2. For every 1 step right, your little staircase goes up 2 steps. And that slope tells us an enormous amount about the road we're on. The sign of the slope dictates the direction. A positive slope, that means we're walking uphill as we move right. A negative slope means we're going downhill. A slope of exactly 0 means a completely flat horizontal road, no rise at all. And a perfectly vertical line? Well, that has 0 horizontal movement, which actually gives us an undefined slope. In real-world terms, we call that a cliff, and yeah, you definitely shouldn't try to walk on it. Meanwhile, the number itself, the magnitude, tells us the steepness. A slope of 5 is a much steeper mountain to climb than a slope of 1. But slope isn't just some algebraic ratio of rise and run, it's intrinsically tied to pure geometry. If you picture that little staircase again, you've essentially drawn a right triangle. The rise is the opposite side, The run is the adjacent side. And from basic trigonometry, opposite over adjacent is the tangent. That means the slope, m, is exactly equal to the tangent of the angle the line makes with the ground. It's just an incredible connection between algebra and the physical angle of the line.
Section 4, Equations of Straight Lines.
Now we can take all that geometric understanding and turn it into usable equations. There are 3 famous forms you should definitely recognize. First, if you only know one single point on the road and you know the slope, you use the point-slope form. By simply multiplying the run to the other side, we get y minus y1 equals m times x minus x1. Second is the all-time classic slope-intercept form, y equals mx plus b. Here, m is always our slope, and b is the exact point where our road crashes into the vertical y-axis. And finally, the general equation, ax plus by plus c equals 0. That one can represent any straight line as long as a and b aren't both 0. Once we have these equations, we can see exactly how different roads interact. If 2 lines have the exact same slope, they're parallel. They are traveling in the exact same direction and will literally never, ever meet. But what if we want them to meet at a perfect 90-degree right angle? Well, they need to be perpendicular. The really neat mathematical trick here is that perpendicular slopes are negative reciprocals of one another. So if one road has a slope of 2, the perpendicular road hitting it at a right angle must have a slope of negative 1/2. Multiply them together and you always get negative 1. Section 5, the derivative connection. We are finally ready to complete our bridge. Everything we've discussed about slopes so far applied to straight lines, where the slope is constant everywhere. But on a curved graph, the steepness is constantly changing from point to point. So how do we find the slope of a curve? We take our little slope staircase connecting 2 points and we start shrinking it. We shrink the horizontal distance, our change in x, closer and closer to 0. We take it to the absolute limit, shrinking and shrinking until those 2 points literally slide together and become just one single point. So the absolutely crucial point here is this. The derivative is simply the slope of the curve at one single point. That is the massive aha moment. It takes the simple algebra of rise over run and phrases it in a single, infinitely tiny moment in time on a curving path. Take a second to look at the mathematical journey you just successfully navigated. We started with basic equations and coordinates. We visualized them on a graph. We searched for roots to find exactly where that graph hit the ground. We introduced slope to understand how steep a straight line is. And finally, we bent that line into a curve, shrank the staircase, and found the derivative, the exact steepness of a curve at one precise point. You have officially crossed the mathematical bridge. I want to leave you with this final, truly provocative thought. If a derivative tells us the exact, precise slope at one incredibly tiny, frozen point on a curve, how can we possibly use that one isolated snapshot to predict where the rest of the entire curve is going to go next? That is the incredible predictive power of calculus, and exactly what you're perfectly primed to explore next. Thank you so much for joining me on this explainer. Keep asking those big questions, and I'll catch you next time.